Today we're going to learn the foundational concept of strings by solving the picoCTF problem, pico strings. It's a bit of a basic problem, but it's going to teach a lot of things that are going to be important to us in the future. In fact, I know several professionals who have made an entire career off of strings. So let's jump in. Starting in the usual way, we'll take a look at what's in the directory. We find the picostrings binary and a readme.md. We'll run the file command on the picostrings file to see what type of file it is. This file is an ELF executable, meaning that we can run it as an application from the command line. If we run it, we see the message, "Have you ever heard of the strings function? Check out the man pages." This is a bit of a clue to the solution. We're going to need to use the Linux strings command to find the flag. One thing that we should talk about before we move forward. It's a bit confusing that there is a strings command in Linux, and this problem involves a binary named strings. So let's clear that up. Most distributions of Linux ship with the strings command as part of the operating system. It's a simple program that searches a file for what it thinks would be human-readable strings or text. This challenge problem is also named strings, but it is not the same program as the one that exists for the operating system. When we refer to the challenge problem file named strings, we will type a // in front of it to indicate to the shell that we want to run the local directory's version of strings. When we want to use the Linux operating system version of strings, we won't prepend a // to indicate to the shell that we want to use the strings command from the operating system. If you want to know how to use the strings command or any command, you can use the man pages by typing man, short for manual, and the name of the command, in our case, strings. Hopefully that cleared some things up, but what exactly is a string? The word string is just tech jargon for a chunk of human-readable text. On all modern computers, characters, numbers, and symbols are represented using numeric values. The encoding that is applied to these characters gives us the mapping between the numeric value and the character that will be printed to the screen. We won't go into detail about the various kinds of encoding in this video, but for now, we will assume US ASCII for the encoding, as it also overlaps with another encoding, UTF-8, though they aren't the same thing. Another thing to be aware of is that these numeric values represent the overall symbol itself, not the way the symbol is stylized. That would be the role of a font. So, for example, when we say that the uppercase letter A is represented by the value hex 41, we mean that the idea of the letter A, not how it's drawn on the screen. The US ASCII range goes from hex 20 to hex 7E. There are more symbols and control codes defined by the US ASCII code page outside of this range. For example, a new line character is hex 0A, which is below hex 20. In addition, some other characters referred to as the extended ASCII range live above hex 7E. But for our purposes, we're only interested in the printable US ASCII range, which is hex 20 to hex 7E. All this means is that a string is just some number of bytes in a row that fall in the printable ASCII range and end in a null byte. By default, the minimum number of bytes that the string command must find in a row for a series of bytes to be considered a string is 4, but that's configurable. It's interesting to note that historically, not all strings followed this format of ending in a null byte. It's the most common way today because of how it was done in the C and C++ languages and the influence that those languages had on other software. However, Pascal's style had a leading byte that would indicate the length of the total string, followed by that many bytes. It had a limitation of a string not being able to be bigger than 255 bytes. MS-DOS also had the idea of using a $sign to terminate strings, but it got this idea from another operating system called CP/M. Let's go back to the challenge. If we run our strings command on the strings binary, we get a ton of stuff. We can pipe the output of the strings command to the less command so we can page up and down through the output and see it better. Some of these strings look like they're nonsense and some of them look like they're base64 encoded data. We'll try to decode the base64 data to see if there's anything interesting inside. Sadly, that looks like garbage. Let's see exactly how many strings we're dealing with. Since the strings command puts one string on one line, we can pipe the output to the WC or word count command and tell it to count the lines with the -L switch. The result tells us that there are over 19,000 strings, which will be too many to reasonably go through by hand. It's possible there's a flag hidden somewhere in the 19,000 strings. To help pare down the number of strings, we'll use the grep command. If you're unfamiliar with the grep command, it's a tool used to search plain text datasets for lines that match a regular expression. We know that most CTF flags follow a specific format of having the word flag, or the name of the CTF event, followed by curly braces, and some text between the curly braces. We know this problem came from picoCTF, so we'll grep for any instance of the word pico. The -I switch tells grep to ignore case. And there's our flag. picoCTF strings saves time. All right, well, that's the whole solution to this problem. It wasn't a very long problem, but we covered a lot of ground. We learned what strings actually were. We learned about the strings command, the grep command, the WC command, and we're going to be using strings and the strings command in nearly every CTF problem that we see from here on out, so it's going to be very useful. If you like the content, please go ahead and like and subscribe. It really helped me out to know whether or not people like what I'm producing. The only problem I really have now is I don't know how to end this video. I guess I should come up with a catchy phrase like, keep on hacking on, or I don't know. We'll see you next time.